Good afternoon, everybody. Thanks for sticking with us. My name is John Walker. I work in US EPA's Office of Research and Development, and I also serve as Secretary of the NADP Executive Committee. I'll be guiding us through the last session of the day, Atmospheric Deposition Effects in Aquatic and Terrestrial Ecosystems. Each presenter will have about 20 minutes. If you would put your questions in the chat box, and we'll get to them immediately following the presentations. Our first presenter today is John Schwartz, and he's going to be talking about through-fall deposition chemistry in the Great Smoky Mountains National Park. Welcome, John. You can share your screen.
Okay, thanks, John. Thank you all for attending the presentation. I'm interested in this project. I've been working with the Great Smoky Mountains National Park for quite some time. And so this is a collaborative effort with Matt Culp and Jim Renfro at the Great Smoky Mountains National Park, and then my former doctoral student and Adrian Gonzalez, and then the student that actually did the work on this project and actually still has a little bit of work to do yet is Andrew Wiedemann. Okay, what instigated this study was that there was a previous study on through-fall deposition that was published by Dr. Weathers in 2006 from data from in the year 2000, and she collected data about 32 sites, mostly kind of in the middle of the park, but then also collected 376 soil sites, and then used this linear correlation with lead concentration in the soils. She also used some NADP and CastNet data, and then used geostatistical mapping to create this figure that you see. And so what you see from the figure, though, is the elevation gradient in deposition from low elevation to higher elevation. So the areas in red are higher in sulfur and inorganic nitrogen deposition. And so they just follow the high elevation ridge line or mountains in the Great Smoky Mountains National Park. But there's been a lot that has occurred since that time. And so we were interested in examining the changes in the park since that period of time. So we, well, from her data, she accounted for in her analysis elevation, slope, aspect, and some vegetation. And the ranges that she observed in the park along this elevation gradient with nitrogen deposition is 4.8 to 31 approximately kilograms per hectare per year. And then sulfur from 6.5 to 41.5 kilograms per hectare. Again, noted it's about 20 years old. Now, we've been collecting data at a high elevation site at Nolan Divide since 1991. Not me myself, but I inherited the project in about 2004. And so we have wet deposition and through-fall deposition through all these years. So we know that there has been changes that have occurred in the park from our data. And so plotting out our data since 1991 with through-fall for sulfate, you can see in the black circles are the through-fall deposition, and then the open circles are the open side or wet deposition. And you can see a major drop in the deposition in 2008. And out of interest, we did actually summarize the local coal-fired plants. They're within 100 miles of the Great Smoky Mountains National Park to the west, and looked at tons per year of the emissions. And the thing that was pretty remarkable about that plot was that in the bar graphs, the orange bars, that it correlated pretty well with the drop in emissions from those power plants to what we were observing in the Great Smoky Mountains National Park. Now, that doesn't say that that's the cause in the park. I think there's multiple reasons. But anyway, it was an interesting correlation. We saw similarly with total inorganic nitrogen. not as a extreme drop as we just saw with sulfate, but again we saw that drop in that time. There was a real threshold in the drop in deposition in 2008, at least in the Great Smoky Mountains National Park. So we know that the data from Weather's study was outdated, and we really needed to see like what is occurring in the Great Smoky Mountains National Park currently. So this should be familiar with everybody. Just again, looking through the NADP data from the United States, and then just crossing that threshold of 2008. I just clipped some photos, and the top two are sulfur, 2005 to then 2012, 2014. And then you can see, obviously, the nationwide, there was this drop between that period. Again, in the bottom two slides, again, nitrogen, not as much, but again, what we're observing in the Great Smoky Mountains National Park was occurring elsewhere in the country, particularly in the East Coast. And then a slide provided by Jim Renfro, he pulled this together as looking at for sulfate, Nolan divide through fall, and we see the drop in through fall. I think it's about 83%, and then at Elkmont site, that's the TN11 site, for wet deposition, about an 80% drop over these various periods that he compiled the data. So you can see that from the bar charts. So we know that there's a drop in deposition in the Great Smoky Mountains National Park. So they see again. So then this is showing the values of 83 and 80% with those two parameters. So our objective of our study was really quite simple. This was Andrew Wiedemann's master's degree thesis. Again, he still has a few little work to do to clean up some things. But we just wanted to know spatially in the park what the deposition amounts were, the deposition loadings were. But we also wanted to examine the relationships with elevation, but also forest vegetation composition in addition. So the objective was just qualitatively compare the data that was collected by Weathers to the data that we collected during a period of 2016 and 2017. So the study design were how we selected our sites throughout the Smoky Mountains. One, we wanted to collect data within these 6 watersheds, which are part of the National Park Service Vital Signs Program, plus the Nolan Divide site. We wanted to collect data on 100 or 1,000-foot intervals and then have different forest types. And we was wanting to have at least 3 to 5 sites per watershed. And we're just limited by resources to be able to collect more. I mean, more data is always nice. And so then we did a geostatistical analysis to identify these locations and met this various criteria, including access considerations as well. Our methods were, we used 3 through-fall buckets set up at each of the sites, and there's a photo to the right that shows our setup. And then we collected data from August 2016 to July 17. And we collect water volume, but occasionally we would have issues with bears, and we had to make some estimates on a few of our samples when the bears would kind of eat our buckets and that. So, and then our chemistry was just some standard procedures. So this is just a map showing the different sites that we collected data. So you can just see, we tried to get a good spatial distribution across the park, and the 6 vital signs watersheds are noted in the slide as you see. So actually just looking at the results, basically we saw a decrease, as you would expect, in sulfur and inorganic nitrogen with the loadings in the order of magnitude. Except there was a few high elevation sites where in inorganic nitrogen that we didn't see quite that drop. But comparing the Weathers data for sulfate loads, her general range for sulfur was 6.5 to 25.9 kilograms per hectare. And then Andrew Wiedemann, from his work, he saw essentially in the range of 1.6 to 3.5. So you can see really quite the difference. And then inorganic nitrogen and weathers 4.8 to 30.9, and then Andrew Wiedemann 3.3 to 8.8. And then in the table for these different watersheds, I did point out for nitrogen, and then the elevations you can see in meters is where there were some cases where the inorganic nitrogen were similar or within the range of what weathers had reported. And so say, for example, like in Abrams Creek, you can see the circles at the top is that she reported a range of 4.8 to 10, and we computed an average of 8.61. And then like Cosby Creek, the one at the bottom, this is a little bit higher elevation at 1,158 meters, same kind of range in nitrogen, and we collected 7.93 kilograms per year. And again, just looking at some of the other watersheds in the park, again, similar, some of the high elevation sites with nitrogen, we saw similar values, but in general, overall, with sulfur and nitrogen, we saw an order of magnitude drop. And so in this group of three watersheds, the comparison was similar to the group in the previous slide. Weathers was 6.5 to 33.6 for sulfur deposition, Andrew Wiedemann 1.5 to 7.2. And then again for inorganic nitrogen, you see 4.8 to 25, and then Wiedemann 1.8 to 9. So looking at the chemistry with respect to elevation, now in this plot that I got from Andrew, the elevation is actually in feet. So sorry about some of the units here, but we see a pH from at the lower elevation, about 1,000 feet, that's slightly above 6. And then at the high elevations at 6,000 feet, we drop below 5.5 or just slightly below 5.5. And then ANC in microequivalents per liter, we're about 100 at 1,000, and then we drop to somewhere around 50 or there below at the higher elevation site. Now these relationships were statistically significant, as you can see in the for pH was highly significant, and then for ANC it was a p-value of 0.002. Now this is chemistry, so not loadings, so concentrations, and again, it's in units of milligrams per liter, should be microequivalents per liter. But anyway, nonetheless, the trend is shown where we see sulfate and total inorganic nitrogen trends along the elevation were not significantly significant across the range in concentrations, but not loadings. So in order to save time, because I know 15 minutes is really quite short, is just to summarize some of the other findings. The plots and a statistical analysis with sulfate loads, we did see an increase in elevation, and that was significant, but then the total inorganic nitrogen increased with elevation, but it wasn't quite significant. We did actually see seasonal patterns, and this was some with elevations that was interesting. The sulfate deposition gradient was most pronounced with elevation during the leaves off period, in contrast to the leaves on period. And then we didn't see a pattern with the total inorganic nitrogen. We also, in contrast, which is helpful for us to kind of understand the overall chemistry, is having the base cation load. It wasn't significantly different along an elevation gradient or seasons for that matter. And then when we looked at this, did some statistics on the forest canopy type, and it was just three. We've kind of classified it into three types: a conifer, deciduous, and then mixed. We didn't see a difference in among these different canopy types with the annual deposition. So, and just in the summary, we see that the sulfur and nitrogen loads generally decreased by an order of magnitude during this period from 2000 to essentially the present 2017. It from Andrew Simon's data that he collected across the park kind of followed the same observation that we observed at our high elevation site at Nolan Divide. We did see through fall pH and ANC decline with elevation. We did see sulfate concentration increase, but then total inorganic nitrogen concentration, we did not. We do see that this gradient with elevation, not with base cations, and there appears to be a strong seasonal effect. And so we kind of want to investigate that a little bit further. And so we do have a little bit more analysis to do. We're doing an additional study with another student of mine looking at some ion canopy cycling, particularly with the base cations, to kind of understand the influence of that on the overall chemistry with the through fall, and then what ultimately ends up into the stream through our soil matrix. So with that, I'll take any questions.
All right, thank you, John. It looks like we do have a couple of questions in the chat window. The first is, with regard to the sulfur gradient with leaves on, do you think that particulate ammonium sulfate is being collected by the leaves?
Yeah, that's probably, I mean, when we see that difference between sulfate and nitrogen, that's probably true. Yeah. Yes.
Okay. We have another couple of questions here. Sarah Nelson says, it's surprising that forest type didn't indicate differences. We saw large differences at Acadia, also studied by Weathers at the same time, were softwoods at specific elevations.
Yeah, I agree. I mean, that's in particular why we in our original study design, we were really looking at that because we expected actually to see a difference. I think I need to dig into that data a little bit more. Like I said, in this summary slide, I want to, my student has finished, but I need to kind of look at some of the data. Well, he hasn't really finished. He hasn't defend yet, but he's finished with his analysis. I kind of want to dig in a little bit more, but yeah, no, I agree. And then the other thing I think that's really important in the Great Smoky Mountains National Park, which I think is our next study that we want to kind of expand on, is there's so much hemlock die-off in the Great Smoky Mountains National Park. We need to really look at the effects of the hemlock die-off. And that was the original goal of this study, was to include areas under hemlock die-off, but we just didn't have enough data points to incorporate that into the statistical analysis.
Great, thanks, John. We have a couple more comments here coming in,
Okay.
and we do have another minute or so. I'll take one more question here, and then maybe you can look in the chat and respond to the others during the next talk.
Okay.
Stuart mentions that it's great to see these repeat measurements, and that the gist of his comment is that it would be interesting to collate them and compare them against the TDEP values, which I agree with. These types of data sets are valuable for those types of comparisons.
Yeah.
And then, oh, I'm sorry, go ahead, John.
No, good comment. Yeah, appreciate that. Agree.
Okay, John, you'll see a few more comments in the chat window there. And in the meantime, we will move on to the next presenter, Justin Fallieri. I hope I came close to getting your last name correct, Justin, but Justin's going to talk about atmospheric nitrogen deposition and declines in native plant richness in the Santa Monica Mountains. Welcome, Justin.
Okay, thanks, John. And that was pretty good. It's Valliere, but that's better than most folks do, so yeah.
Okay.
Okay, is this displaying correctly now?
It sure is.
Okay, great. Like the previous speaker said, I do this a lot teaching, but I never really see what it looks like on the other side. So, all right, so today I'm going to talk about some of my PhD work, which was looking at nitrogen deposition effects in the Santa Monica Mountains of Southern California. And then I'll talk about a few follow-up experiments that I did during my first postdoc at UCLA as well. So just want to give a shout out to my co-authors first. So Gary Bucciarelli is a colleague at UCLA, and he helped with some of the tree regression and random forest regression models that we ran. Anjay and Mark are both at the US Forest Service and were really instrumental when we were first setting this project up in 2011 and 2012. The project really happened because Irina Irvine, who was at the time the restoration ecologist for the Santa Monica Mountains, her and Edie Allen wrote a grant to the Air Resources Division of the National Park Service and got funding for this. So that really funded a big bulk of my PhD work. And then Bob Johnson at UC Riverside did a lot of work in GIS with some of the modeling that we were attempting to do that didn't pan out the way we were hoping to, but I'll talk about that in a little bit. So overall, the goal of a lot of my research and most of my PhD work was to look at how nitrogen deposition will impact California's coastal sage scrub. And so coastal sage scrub, it's a very literal name. So it's coastal, it grows along the coast from Baja, California, all the way north of the Bay Area. It consists of a lot of sage species in the Lamiaceae, as well as sagebrush, which is in the Asteraceae, but has that nice similar sagey smell. And it's a scrubby shrubland habitat. So it's arguably one of the most impacted and threatened ecosystems in the United States. So it's estimated that about 90% has already been lost to development. And what remains is subject to high levels of nitrogen deposition in parts of the state, also subject to impacts from invasive species and increased fire intervals and other factors. So a lot of great work by Edie Allen and other folks, so George Verlitis and Sarah Kimball at UC Irvine and other folks have done a lot of really great work in coastal sage scrub looking at nitrogen impacts. But surprisingly, there wasn't a whole lot of data out there on actual patterns of species diversity across anthropogenic gradients. So a lot of the work that had been done was in fertilization plots, but surprisingly not a lot looking at real gradients. And that's just true for Mediterranean type ecosystems overall as well. So we were looking at nitrogen deposition effects, but the work also happened to coincide with the extreme drought in California. And we're interested in interactions between these two factors and non-native plant invasion. So as you can imagine, nitrogen deposition is a big problem in the LA area and in Southern California. So this is showing the CMAQ model data. So we can see that there's a range of, ambient less than 3 kilograms per hectare per year in areas that get greater than 25 kilograms per hectare per year. So the Santa Monica Mountains are in this area here, north of Los Angeles. So you get a nice gradient of cleaner sites all the way to really end polluted sites out by Griffith Park and Runyon Canyon. So we wanted to kind of fill that research gap looking at diversity and look at how plant richness of this ecosystem might change across that gradient of the Santa Monica Mountains. The Santa Monica Mountains National Recreation Area was established in 1978, and it was actually established to be what they called an airshed for the city of Los Angeles, to have this park that was protected from all the terrible smog at the time. But of course, park boundaries can't stop air pollution from coming in, so it's still a significant problem for parts of the park. It's also the largest urban national park in the country and in the world, depending on how you measure that. And it's unique in that it consists of both federal and state parks, as well as other municipal city parks. Okay, so we ended up going with the CMAQ modeled values for deposition for our analyses. So we did do work with through-fall collectors, but had terrible luck. We had them out for different periods throughout 2 years, but this was during the drought, and so what was ending up in the funnels wasn't ending up in our columns, and we had problems with vandalism and other issues. So we ended up going with the CMAQ model for this paper. We did do atmospheric monitoring as well, and it mirrored this gradient that you can see here, where we got low values out on the western end of the mountain range and much higher values approaching 20 kilograms per hectare per year at those sites closest to the LA basin. So what I'm showing here is different measures of soil nitrogen. So we can see that there's a strong positive correlation between that modeled nitrogen deposition and total extractable nitrogen in the soil. That's mostly due to nitrate in the soil, but also to a lesser extent ammonium. And we also saw significant declines in the carbon to nitrogen ratio. So it seems like the CMAQ model actually does a really good job if we look at the soil nitrogen values to understand this N gradient. Okay, so what we found when we measured plant community composition at all these sites was a significant reduction in the number of native species, so native plant richness. And this was driven mostly by a loss of native forb species. And so this was true when we looked at total richness per site across the gradient, and then also when we looked at mean plot richness. So what I'm showing here is the mean plot richness. But so at the site scale and at the plot level as well, we get a reduction in those native forb species. And these are just images of some of those native forb species in coastal sage scrub. This actually came out, I haven't pressed here because I forgot to update this slide, but this came out earlier this year in Ecosphere if anyone wants to read that. We also saw some evidence for simplification in the actual shrub community, so the woody plant species. So this was a significant, weaker trend, but this was the mean number of native shrubs per plot. So it suggests there might also be some simplification in the shrub community. Because these species are longer lived, we kind of speculated that it could be that the changes that we see for those shorter lived herbaceous species just haven't manifested in these older shrub communities. And then finally, we found evidence that nitrogen deposition is associated with greater non-native cover. Most of these non-natives were invasive annual grasses and invasive annual forbs like centaurea and mustard species, things like that. So overall, the non-native cover made up a pretty low percentage of cover at our sites. And that's because we did try to find the best intact mature coastal sage scrub at each site. But even in the best remaining CSS across the park, we do see a significant increase at the more polluted sites. And there were negative relationships between non-native cover and our measures of native plant richness. So even though non-native cover is low, it seems like it is perhaps driving some of the lower native plant richness. And that makes sense based on previous work in this system and in other ecosystems. So that's all great. It does appear from these data that nitrogen deposition is associated with decreased native species. But this gradient isn't perfect like many landscape level gradients because there's a lot of other factors like precipitation, elevation, soil type, fire history that differ really dramatically across these sites. Well, some of these variables more dramatically than others. Soil type in particular in the Santa Monica Mountains is really messy. The geology is like a jigsaw puzzle of different parent materials. So we did kind of want to understand how these other factors might be influencing those patterns of plant richness on top of the effect of nitrogen. This is just showing a correlogram of all these different measures of the plant community, multiple measures of soil chemistry and nutrient availability, fire history, then we have nitrogen deposition, soil N. So we can see that there are multiple variables that are co-correlated here. So what we did is to get at this was we used regression tree and random forest analyses. So this uses an iterative and binary recursive partitioning method to develop a model that's the best predictor for your response variable, which in this case, we looked at total forb richness at the 30 sites and then mean forb richness per plot. And so this is the results of the regression tree. And for both of these variables, soil nitrogen was the primary, most important explanatory variable and explained most of the variation in forb richness. These other variables, so soil pH, elevation, native forb cover, and then sand, explained very little variation in the data. And this is the output from that random forest model. So soil nitrogen, again, was the biggest or most important predictor of native forb richness. Other factors were significant though. So hotter and drier sites tended to have lower plant richness independent of nitrogen deposition. And then nitrogen deposition was also picked out in these models too. So yes, nitrogen deposition seems to be important, but other factors like aridity or non-native plant cover also have an effect and may interact with nitrogen deposition. Okay, so just a recap of this first part. So nitrogen deposition does appear to reduce native plant richness. This is likely partially because of increasing non-native cover. We get a loss of native forb species in particular, and maybe some evidence for a simplification of the shrub community. Invasive annuals grow larger and produce more seed and exhibit greater nitrophily than native wildflowers. So I'll show some data shortly on that. So that's one of the mechanisms I think that causes this. And then the relationship between nitrogen deposition and richness appeared to be somewhat linear. So we couldn't really get at a critical load for this ecosystem, which previously has been estimated at about 10 kilograms per hectare per year. So I think we would need to look at more sites to see if that critical load holds true for this ecosystem based on forb richness. So I just want to talk briefly about some mechanisms that might underlie these patterns. So we did do some experimental nitrogen addition work as well at this site. So this was at one of the clean sites on the west end of the gradient. So we had a experiment with 0.5, 1.5, and 3 grams of nitrogen per year. So this corresponds well to the actual gradient you see in the LA area of nitrogen deposition. Like I said earlier, this work coincided with the epic drought in California, so that became part of our experimental design, whether we liked it or not. And what we found is that nitrogen deposition seemed to exacerbate drought-induced shrub mortality during that time. So we can see that at the end of the study, the high nitrogen plots had the lowest native shrub cover, and they had the highest % mortality in these plots. And we think this was partially true because that added, due to the fact that that added nitrogen decreased the water use efficiency of native shrubs. So even though the shrubs were dying back at the plant level, they were still producing more leaf area at the terminal branches, which is interesting. So it seems like these shrubs just kind of can't help themselves when they get added nitrogen. And that leads to lower water use efficiency and perhaps higher risk to drought. And then we saw similar patterns where the high nitrogen plots had higher non-native cover. So it does seem like added N negatively impacts native species because it positively impacts these invasives. We also looked at some physiological mechanisms. So that work with the water use efficiency suggested to us that there might be trade-offs between growth and water use that differ in native coastal sage scrub species and invasive non-natives. So typically we expect there to be a trade-off in these traits if we look at water use efficiency on the x-axis and growth rate on the y-axis. So plants that grow fast are less conservative with their water and vice versa. And then Sarah Kimball did some previous work that suggested that maybe some invasive species are able to escape this trade-off. So we were interested in looking at that under nitrogen deposition and drought. So we looked at this in native coastal sage scrub species and then invasive annuals. This was because of the drought, we ended up doing this in a glasshouse experiment where we grew little community mesocosms and then controlled water inputs and nitrogen inputs. And what we found is native species do indeed seem to experience that trade-off, negative trade-off between growth rate and water use efficiency, but invasives don't. So invasives almost always had higher growth rates and higher water use efficiency than the natives and didn't experience the trade-off. this is just showing this where each plot is a species, or sorry, each dot is a species too. So you can see that the yellow, the invasives, do kind of separate from the green, which are the natives, regardless of resource availability, but especially under high resource conditions. Okay, so why does nitrogen deposition reduce native diversity while promoting invasion? Just a couple other potential mechanisms. One of my students at UCLA, when I was doing a postdoc there, just looked at growth of native annuals and invasive annuals under high and low nitrogen. And she just found that overall the invasives just tend to grow larger, but that's especially true under high nitrogen availability. So it does seem like the invasives are more nitrophilic than the native species, which is what other folks have found in other systems as well. Evelyn Escobedo did a similar experiment, but she looked at seed production under drought and well-watered conditions. These are just some fabulous images of the seeds that she took that I couldn't help but show you all. And so what she found is under well-watered and drought conditions, invasives just grow larger and produce more germinable seeds. If we repeated this with nitrogen too, we would expect to have even higher seed output under high nitrogen conditions. Okay, I am running a little bit out of time, I feel like. But I just want to talk real briefly about a couple final experiments. So ED has done a lot of work looking at effects on mycorrhizal associations under nitrogen deposition. So we also explored some mechanisms that might be related to plant soil feedbacks. And this is just the idea that plants have an influence on the biotic and abiotic properties of soil, and those changes below ground can feed back into above ground patterns. And resource conditions like nitrogen availability can alter those relationships. So in one study, we found that soils from low deposition sites, so the low dep inoculum, offer more protection against drought than high deposition soils. So this is comparing these to sterile non-living soil. If the plant soil feedback is above 0, that means there's a positive response. If it's below 0, it's a negative response. So these low deposition soils promote a positive feedback under drought, so they can help plants under drought. But nitrogen impact soil communities don't seem to be able to offer that same protection. And we did a similar experiment where we grew 3 invasive species in low deposition, high deposition, and then sterile soil as well. And in all 3 species, we found that the greatest growth occurred in the high deposition inoculum and under high nitrogen availability. So same thing for Centaurea, and same thing for Hirschfeldia, which is an invasive mustard. So it does seem like the changes to plant soil feedbacks favors invasive annuals over native species. Okay, so this is just a recap of those mechanisms. So enhanced soil nitrogen due to end deposition promotes the growth of invasives. There seem to be differential effects of end deposition and drought on natives and invasives, where the natives suffer physiological trade-offs that the invasives don't, and also altered plant soil feedbacks may promote this effect as well. Okay, with that, I'd just like to thank all my collaborators and especially the Air Resource Division for funding most of this work, and I will take questions if I have time.
Thank you, Justin. That was an excellent talk, just an enormous amount of work represented there.
Sorry if I went a bit fast.
No, that you're okay. I think we have time for one question. I'll just take the top one on the list here from Mike Bell. Are there similar coastal sage scrub communities that exist in the deposition gap from 2 to 8 kilograms of your data that you could use to supplement this data set?
Yeah, that would be great if we could go back and have more sites within that range. But it was actually even finding those 30 sites in the mountain range and matching them for like slope and elevation was like a big challenge. So I think there's a lot of positives about the Santa Monica Mountains being a good study system, but there were also some challenges in getting good sites as well. So I think if we had more sites and more in that lower range, we could definitely get at that idea of critical loads better. So. Mm-hmm. Now that I'm back in Southern California, who knows, maybe I'll start exploring that a little bit more.
Great. Thank you. And you'll see a few more comments and questions in the chat box that you can
Cool.
you can take
I
a
can
look
stick
at.
around for a little bit, but then I have to teach, so I'll try to answer some of those. But folks can email me if they have any questions about this too.
Okay. Thanks,
All right.
Justin.
Thanks, John.
Okay, we'll move on to our next presentation by Per Erik Carlson. Per will be talking about total deposition of inorganic nitrogen to Norway spruce forests. Welcome, Per.
Okay, thank you very much for this opportunity to present some results from Sweden regarding nitrogen deposition to Norway spruce forest. First of all, I'd like to say that I'm very impressed by this NADP network. I've been working in Europe with the conventional long-range transport of air pollutants for many years, but I think that you in the United States, you are ahead of us now concerning the quality and quantity of deposition monitoring. Okay, in any case, I will present some recent data on, we are trying to estimate total deposition to Norway spruce forest. And you should acknowledge my co-authors here. We are all from the IVL, Swedish Environmental Research Institute in Gothenburg, Sweden, except Cecilia Axelsson, who is at the Lund University. The aim of our work is to correctly determine the dry and wet deposition, nitrate and ammonia to Norway spruce forest. But we also like to have an estimate of what we call the canopy exchange, that is the direct canopy uptake of nitrogen in these Norway spruce forests. So first, a short introduction. I hope you all know where Sweden is, and a little bit background about land use in Sweden. We have a long land area spanning the latitudes between 55 and 69 degrees. So it's long country in the northerly direction. We have a total land area of 41 million hectares, of which 21 million is forests. We are a forested country, and the agriculture that we have is located to the south. The air pollution situation is strongly depending on the long-range transport of air pollutants from continental and southern Europe, as well as the United Kingdom. So of the deposited oxidized nitrogen in Sweden, 90% will originate from sources outside Sweden. And for reduced nitrogen, it will be about 70%. So we have a strong air pollution gradient from the southwest towards the north. So the aim was to develop a new method to correctly estimate nitrogen deposition to this Norway spruce forest, because, as I indicated earlier, we know that we have a direct nitrogen uptake in the canopies. So we know that the throughfall is not always working when we're trying to estimate the nitrogen deposition. In fact, in northern part of Sweden, the deposition in the throughfall will be lower than the wet deposition to the open field. So we made use of monitoring plots within this Swedish throughfall monitoring network. This network has been operating since 1985. So we now have 35 years of data. But these measurements that I present now has not been operating that long. So we are using 10 of these plots that we have over Sweden to, these are equipped then with both throughfall deposition equipment and bulk deposition equipment. And then in addition, we have these equipment under the roof here in the left photograph, which we call the string samplers. And these sites are all positioned in the rural background areas, so there are no major emission sources in the vicinity. And sampling is made monthly year-round. And you can see the publications down to the left where we have described this monitoring system. This method was actually developed by Martin Ferm and Hans Hultberg in the 1990s. And the idea is to use a combination of the net throughfall of sodium to the forest and the dry deposition that we measure to this Teflon string sampling equipment that is placed under a roof. So the idea is that the dry deposition of sodium, the net throughfall of sodium, is going to reflect the physical properties of the forest canopy, for example, the leafy index and so on. And then we multiply this by the ratio of the component that we are interested in, the ratio to sodium. So by this an approach, we get the dry deposition of this component that we are interested in to this nearby forest. So net throughfall of sodium multiply by the ratio, concentration ratio of the element to that of sodium. That's the approach. Of course, there are some assumptions then associated with this method. And the first one is that the sodium is biologically inert. So we assume that there's no interaction between sodium and the forest canopy. And the other major assumption is that the ratio of dry deposition of this element that we are interested in to that of sodium, this ratio will be the same for the Teflon strings as for the forest canopy. And the Teflon strings are, as the name is, it's made of Teflon, so they are hydrophobic, and they are strings with about 1 millimeter diameter. But we realized that we are mainly sampling the particle bound dry deposition with this method. So I will show some results now, and I will use a geographical index, which is very useful for us because, as I said, there is a gradient in air pollution load from the southwest towards the north. So we use the index latitude plus longitude, and that index would increase from southwest towards northeast. So these are results from 4 years of intensive measurements at these 10 sites across Sweden. So in the upper row, you have nitrate, nitrogen, and in the lower row, you have ammonium, nitrogen. And the left column is the total deposition in absolute values in kilograms nitrogen per hectare per year. And the right column is the share of dry deposition to total deposition. And we see that we have a good correlation with this geographical index, longitude plus latitude. So in the south, we have a deposition, total deposition of up to 10 kilograms of nitrogen, and even higher some years for ammonium nitrogen. And the share of dry deposition in southern Sweden to the left in this diagram is roughly between 30 and 50%. So it's a large fraction of dry deposition. And then the deposition declines towards the north. So in the far north, we have about 1 kilogram nitrogen deposition per hectare per year for each of nitrate and ammonium. And also the share of dry deposition will decrease towards the north. So that means in total in southern Sweden, we have a deposition of between 15 and 30 kilograms of nitrogen per hectare per year to these Norway spruce forests when we summarize the dry and wet deposition. Then we were interested in estimating this canopy exchange, this direct canopy uptake of inorganic nitrogen. And we did that by subtracting the throughfall deposition from the total deposition. So the difference here will be the canopy uptake. And again, this is plotted towards this geographical index from southwest towards the north. And the site that is most to the south shows a negative value, and we think that is depending on that we are actually underestimating the nitrogen, the ammonia gaseous nitrogen deposition at this site. So that is why this difference is negative for this site, we think. Of course, it's a possibility also that there's a leakage out of the canopy, but we don't think that it's so likely. And then we have optimum curve. So in the mid-Sweden, there is uptake in the canopy around up to 6 kilograms of nitrogen per hectare per year. And then it declines towards the north. And I think this is the balance then between the nitrogen availability, because in the north we don't have more deposition than around 1 to 2 kilograms of nitrogen. But in the south, the decline there could be a sign of nitrogen saturation in this kind of Norway spruce forest. So that was for those 4 years. Now we have tried to reconstruct the total deposition for a 20-year period, starting in 2001. And the thing was that we had, well, if we start with the wet deposition, I didn't say that, but we used the bulk deposition, and then we corrected this based on a number of years with measurements where we have this bulk deposition equipment placed under a roof, and compared to that with the nearby measurements without a roof. So we have a method to correct bulk deposition to wet deposition. So we have a wet deposition for all these years. But then for the first year, for the first period, 2001 to 2007, we had this Teflon string measurements, but we had roof of plywood, and we afterwards discovered that there was sometimes a leakage of sodium out of this plywood roofs. So we have to recalculate this dry deposition based on magnesium instead, and then we converted this to a sodium basis with the parallel measurements estimates for some years. Then we had a period 2008 to 2013 when we did not have any dry deposition measurements. So for that time period, we have interpolated the dry deposition. And then again, we started the complete measurements in 2014. So, and then we made use of all measurement sites with the bulk deposition measurements, which are these small black dots on the maps. So we could show that there was a geographical pattern in this share of the ratio of dry deposition to total deposition of nitrogen. I showed that in the previous slide. So we could use that to estimate the dry deposition also in all sites where we had bulk deposition only. So we could generate this kind of maps over Sweden for different years with the deposition. And you can see the strong gradient. And from this, we could calculate the trends for total deposition of inorganic nitrogens for 3 different regions based on these maps that I showed in the previous slide. So we have one region for southwest Sweden in the green, southeast in the red, and north in the blue. And the gray line is the reported emissions of inorganic nitrogen from the European Union, EU 28. So this is the sum emission of nitrogen from these countries. So we can see that the trend in there is a significant decline in the total deposition of inorganic nitrogen over this almost 20-year period, and the decline is in line with the reduced emissions from Europe. So we think that this is quite nice. So the take-home messages then will be that we have a total deposition of inorganic nitrogen to Norway spruce forests that is relatively high in the south, and we apply a critical load for nitrogen deposition to coniferous forest in Sweden of 5 kilograms per hectare per year, and that is exceeded in the southern part of Sweden still. And we then have a 30% decrease over this almost 20-year period, in line with the decrease in the reported European emissions. And there was a direct nitrogen uptake to this Norway spruce canopies that ranged between 1 and 7 kilograms nitrogen per hectare per year. So thank you very much.
Thank you, Per. Very interesting talk. Thank you for joining us today. Are there any questions? We have one question in the chat box from Rogelio. Industrial activities in the south compared with north ones.
Yes, there are some. There are more traffic and more industrial activities in the southern part, but still the major impact even in South Sweden is from long-range transport of air pollution from continental Europe. And all these sites that I showed, they are not close to any point sources.
Okay, we have another question here from Greg Weatherby, a comment and a question. It's refreshing to see dry deposition measurements. NADP does not do that yet. Do you have comparisons between measured and modeled dry deposition based on emissions?
Yeah, we have a published study on these results, and in that study we compared with the modeled deposition, both with the EMEP model, which is used on the European level within the Air Pollution Convention, and also with the MATCH model, which is used in Sweden by the Swedish Meteorology and Hydrology Institute. So we have a good match between modeled and measured values.
Okay, I think that also addresses another question that we had from Amanda Cole on how do your measurement-based total deposition maps compare with those from MATCH?
Yeah, they correlate relatively well. Of course, when you do modeling, you have only what you put into the model, so you cannot include exceptional events. For example, in 2014, we had exceptionally high nitrogen in the south of Sweden, which the models could not predict. So and we really don't know exactly what the source of those high deposition values were. So as always, it's good to combine the models with the observations.
Couple of other questions here. One from Tanya Williamson. Is the noise in the south related to mixed land use or mixed management practices?
Yeah, and again, the big uncertainty here is the dry deposition of gaseous ammonia, which we don't think we include. There could be a fraction of that is taken out by these string samplers. So that, and we have only the high air concentrations of ammonia is for the south of Sweden, so that could be a little bit part of this. Otherwise, I think, well, it's the direction of the air masses, how they move, and so on. So there are also large-scale differences between years, for sure.
Mm-hmm. Thank you. We have one more question on the string sampler methodology, which I was curious about myself. I think you mentioned that it primarily samples particulate species, and you mentioned just now that there would be an underestimation for gases like ammonia. Has the string sampler, and this is a question from Donna Schweedy, has that string sampler been compared with other flux measurement methods?
Not really, not besides modeling. I don't know of any other measurements that we can use to compare. There are, of course, micrometeorology sites, but there are very few, so we don't have any co-location with our measurements with those few micrometeorology flux sites. So we don't have any, as far as I know, possibilities to compare.
Okay, thank you, Per. I think those are all of the questions. We'll move on to our next speaker, which is, I believe, Kevin Bishop. And I think I'm correct that we're going to play a recorded version of Kevin's presentation, and then he may be available to answer some questions afterwards.
Greetings from Sweden. This is a country that has great plans for using the forest to achieve a carbon neutral future. The question is the use of the forest exceeding the critical loads? What I'm going to talk to you about now is a 7-year project looking at key to this science.
You're not hearing anything, are you?
No.
No.
Okay, I'm working on it here.
Thanks, Bob.
One of the great successes.
Now we are. Well, we were briefly.
One of the great successes.
That's it.
One of the great successes of science supporting policy is the way that the concern about acid rain has led to a remarkable reductions in sulfur emissions and sulfur deposition.
We lost the audio again.
Especially.
Did it come back?
No.
Across Europe, where we're back to levels that haven't been.
There it is.
Seen since a century ago. Key to this science policy success was the acceptance of critical loads as the basis for reducing acid emissions. The basis of critical loads were the estimates of weathering that science was able to produce. The weathering that could balance the acid deposition and the biomass harvest. Ironically, the science that was behind weathering became a victim of its own success. After a decade of great interest in weathering, the political agreement on achieving critical loads meant that the impetus for doing more with weathering evaporated overnight. Thus, it looked like weathering researchers might be going the way of zeppelins and dinosaurs. That, however, would be a very unfortunate development because the nature of acid deposition and the need for critical loads is changing. In the 1900s, the last century, acid deposition in Sweden was roughly equal to forest harvest in terms of the pressure it put on, the acidification pressure it put on soils. But now, in this century, acid deposition has declined, but forest harvest is increasing. It's supposed to increase more. Thus, the acidification pressure is much greater from forests than from acid deposition. Now, back in 1980, in the heyday of weathering research, acid deposition and biomass removal put the deposition way above critical loads. But now, with the great decline in acid deposition, we are around the critical load, even with what's left of the acid deposition and what we have for forestry. Question is, are we really at that critical load, just above it or below it? The uncertainty in the estimate of weathering is now large compared to the management decisions we have to make, especially about sustainable forestry in the future. Is that critical load that current models say is being exceeded by forestry really the right critical load or not? This is where the Quartz project, quantifying weathering for sustainable forest management, comes in. Sweden is using a modeling platform based around the Profile Forsafe set of models. These are the models that indicate that forestry is not going to be sustainable because it exceeds the critical load. Question we had was, is the uncertainties in this model platform, can we reduce them to make sure that we're confident? And are there some errors lurking somewhere in the modeling platform that mean that we might have actually underestimated the amount of weathering that exists? This project was sort of a chance for those of us older members of the team to become like the space cowboys and come back and go on one death-defying mission impossible to quantify weathering. A little bit easier, maybe, than blowing up an asteroid coming in from. Quartz had 3 questions. How much weathering is there for the trees? How much weathering is there for the fish? And will climate change and forest harvest actually change the amount of weathering product that's available? To tackle these questions, we compared the profile model, this platform that is the basis for the official Swedish critical load estimates, with other independent approaches. We looked at specific process representations, in particular whether there were biological or chemical feedbacks missing from profile that might result in underestimates of weathering. This involved microcosm and mesocosm experiments, the use of isotope tracers, and a new simplified profile platform. We used the more sophisticated HD Mintech set of models for better comparing individual process descriptions. And some of the things we looked at were base cation and aluminum binding reactions, mineralogical determination, the integration of weathering to the catchment scale. These were all tried to be linked to sustainable forestry, including national upscaling, weathering estimates, and what might happen with whole tree harvesting. So, what did these 7 years of studies find? Regarding the biology, if trees were limited in their phosphorus supply, the trees could activate weathering to get at phosphorus in minerals. But if nitrogen was limiting, and nitrogen was limiting in most of the Swedish forest landscape, the trees could not turn on any extra weathering. So biology is included in the Profile Forsafe, as included in the current modeling platform, appeared to be about what biology can offer in the way of supporting weathering. There wasn't an extra high gear that biological feedbacks could turn on. Another area we looked at in the model, in the project, was comparing different models, because earlier studies had often shown great variability between different models' estimates of weathering at a site. We found that harmonization of the input data and the system boundaries reduced the differences between the independent modeling approaches used at specific sites. Correlations between the different approaches across multiple sites suggested that the key processes were not missing or incorrectly defined. Another modeling approach, the decadal scale mass balances, did, however, seem to be very susceptible to uncertainties and are not appropriate for the type of weathering estimates that are needed in critical loads. Then there was the detailed look at model processes. The profile modeling platform doesn't use the absolute state-of-the-art descriptions of base cations or aluminum binding reactions, so they were compared with this HD Mintech model. They found there were differences between the more sophisticated model and what was in profile, but the differences were usually relatively minor, although the pre-industrial concentration of adsorbed base cations is overestimated when using the profile set of models. Another thing that we found was that the chemical breaks when a weathering process gets towards equilibrium were something that were not implemented satisfactorily in profile. That had implications for the next area we looked at, upscaling from a soil profile to a catchment and was delivered to a stream. In Scandinavia, aquatic ecosystems are some of those most threatened by acidification. But much of the weathering research that has been done in the Nordic environment is focused, takes us to the last step in the quartz research program, scaling up from plot scale studies and laboratory studies to the landscape scale and climate change. The national weathering maps made from the profile platform were compared with the historical weathering method across the country. The gradients and resulting weathering rates were similar within the routing zone. Using profile with different climate scenarios predicted that increased weathering rates at higher temperatures would not counteract the increased base cation losses associated with the intensification of forestry, except in the very northern part of Sweden. So, when we look back at quartz, the 7 years, could we say that we've gone from mission impossible to improve the estimate of weathering rates for critical loads across Sweden to mission accomplished? We look carefully at the profile modeling platform. We were not able to find any obvious mistakes in it. It certainly does not seem to be overestimating the amount of, does not seem to be underestimating the amount of weathering that is coming out of the Swedish landscape. That means that the projections that the base cations in Swedish soils were likely to be depleted if forestry is intensified in the future, especially in southern Sweden, seem to be valid. That is something that's going to have to be taken into account as Sweden plans its future bioeconomy. But there are two critical load caveats that I would like to leave you with. One is that stream acidity needs more than just low base cation concentrations in the soils to create acidification that threatens fish. The mobile anion is critical for lowering the pH and releasing aluminum. This is something that we've looked at carefully. We see that our soils are going to become more depleted in base cations, but we simulate what the water chemistry is. It doesn't mean we're going to be getting acid episodes or lowered pH, because that mobile anion provided by acid rain isn't there anymore. Of course, sea salt episodes, it will be certainly less buffered surface waters, but there isn't that mobile acid anion from acid rain. Something to keep in mind as we look to the future. Another thing to be aware of is that the base cations available to the trees are underestimated by the methods that are used in estimating what is in the soils. There are many different ways to extract base cations from the soils. And a study that was done in our project and other studies that have been published recently show that those trees do appear to have access to stores that are not accounted for in current estimates of the supply that is there. Of course, the amount of base cations in the soils will decrease when the critical loads are exceeded. But when those decreases in the store become critical for the tree's survival, or their health, that is another issue. With that, my presentation, my pre-recorded presentation, comes to an end. I've enjoyed very much the chance of these last 7 years to revisit questions I came to work on 35 years ago. That's me in that picture. I don't have as much hair. What little hair I have left is much grayer, but it's been great to reach some closure in some of these questions that seemed so perplexing so many years ago. I'm glad to have been able to share this project with some colleagues who were working on this in the 1980s, but also a younger generation who did their PhDs in this project. If you have questions, I hope that the link to Sweden will work so I can answer them. But if not, or if your questions are more than I can answer in the next few minutes, please refer to the special joint issue of the EGU journals, Biogeosciences and Soils. Thank you. And that's it.
Okay, I think Kevin is with us now. I think he's on a train traveling somewhere. Kevin, are you there?
I am here, if you can hear me.
I can hear you. Yes, thank you for being with us. I know you've got some difficult logistics there, and you pre-recorded your presentation, and thank you for that. Are there any questions for Kevin? Okay, I don't hear anyone speaking up, and I don't see any comments in the chat box.
Good. That's what I like in a course. That means that every student understood everything I said. I like that. Thank you.
Well, some questions may pop up here momentarily, and if so, you can check there.
Good.
Again, thank you for joining us, and I hope the rest of your train ride goes well.
Good. Thanks. Bye-bye. Good night.
Thank you. Okay, our next speaker of the afternoon is Tanya Williamson, and she's going to be talking about water resources in a changing world. Welcome, Tanya. Our next speaker is Karen Riva Murray, and she's going to talk about mercury and fish from streams and rivers in New York State. It's all yours, Karen.
Thank you. First of all, I want to acknowledge my co-authors, and also, is there a way I can minimize this? I'm just going to minimize this. I don't know, can someone help me out? I'm seeing everybody on here and it's taking up most of the screen. But
oh, interesting. Okay, well, we can see your slides just fine, but it sounds like it's impacting you.
Can you see me in the little corner there?
Yeah, we can see you, but it's in a small little box.
Okay, we'll leave it at that then.
Okay.
So, okay, so I want to acknowledge my co-authors on this study, and also NYSERDA, New York State Energy Research and Development Authority, which funded this study. And a little bit of a rationale for the study. New York State has more than 100,000 kilometers of streams and rivers. And the fish in these streams and rivers are a potential source of elevated dietary mercury to humans and wildlife. However, previous descriptions of statewide distribution of fish mercury in New York have focused mainly on lakes and similar habitats. And there hasn't really been anything on streams and rivers as far as looking at broad distribution of fish mercury. However, there's been a lot of data collected on fish mercury from New York streams and rivers over the years that can be used for this purpose. So the objectives of this study are to describe stream fish mercury distribution across the state with existing data, examine some of the biological factors that influence these patterns, and also identify some important environmental drivers. And this is based on a paper that was recently published in Ecotoxicology. It was published online, and a print issue is coming out soon, a special issue on mercury in New York. So we had various criteria listed here for data compilation. I want to point out just a couple. So these were all from freshwater streams and rivers in New York. And we we decided on 2007 to 2016 as a 10-year period that basically was going to be sort of a snapshot in time. And we selected studies that were based on a broad coverage across the state, or data sets that had an intensive coverage within a particular region. We didn't try to pick out studies of like individual sites. So we had 5 major data sources, and they're shown here. And most of the samples and many of the sites came from New York State Department of Environmental Conservation. And all in all, after combining a few nearby sites with each other, we had 220 sites and more than 3,000 samples to work with on streams and rivers in the state. So there were some challenges in analyzing these data. First of all, the data set contained many species, and the species varied widely across sites. So we didn't have a lot of consistency in species across the sites. There were large size ranges within species that were collected across the sites. And there were many sites with relatively few samples, maybe like 1 to 3 samples at many sites. So our approach was to combine species and broad size classes that we formed into what we call functional taxa. And we then selected certain functional taxa that were more widely distributed, and we mapped these in relation to human health guidelines and wildlife guidelines. And then, in order to use more information from more species across the state to look at some of these patterns and some of these drivers, we collected what we called a Mercury site score. And this was based on a scaled Mercury index for multiple functional taxa, and I'll explain this just a little bit more. So basically, we selected some of these functional taxa, again, species, size, class combinations. We selected ones that are more widely distributed across the state, and also that had a range of mercury concentrations. So we avoided species or size classes that were like pretty much high everywhere or pretty much low everywhere. We wanted ones that had a good range of mercury concentrations. And we calculated a mercury index scaled from 1 to 10 for each of these selected taxa and the index across the sites. Then we derived a fish mercury site score so in other words, we ranked the mercury concentration and then scaled it from 1 to 10 for each taxon. Then we derived this fish mercury site score as the median for all the functional taxa that were present at a particular site. And so basically in the long run, we calculated a site score for 170 sites based on anything from 1 to 8 functional taxa per site. So now getting back to just looking at mercury concentration ranges in relation to guidelines. This is looking at some sport fish in relation to guidelines for sensitive populations, the US EPA criteria of 300 nanograms per gram, and a couple of arbitrary higher levels. And here we're looking at we combined black bass species we've got 2 functional taxa here, black bass species that are smaller and larger. So here's the map of New York showing the smaller black bass species, mercury concentrations in relation to these guideline levels. We can notice a couple of things. They exceed, so these are predatory fish. They exceed 300 nanograms per gram and also higher guidelines at many sites. But we do see some regional differences with what we seem to see as lower concentrations in the western part of the state. Now we're going to look at the larger functional taxon of black bass species. And we notice a couple of things here, a similar regional pattern with the lower concentrations in the west. But in general, the concentrations in these larger size classes are higher than the smaller size class. And also we're seeing somewhat less spatial variation in the larger, more piscivorous size classes. And this pattern tends to apply to most of the species that we looked at. So now we're going to compare an invertivore, some salmonids, and a top piscivore, the walleye. These are large walleye. Again, compared to human health guidelines. And with the salmonids, we notice that we have relatively low mercury at most sites, but not all sites. We see the higher concentrations in the Adirondacks, northeastern part of the state, also in another highland site down there east of the Albany area. Now we're looking at walleye. These are very larger, older, piscivorous fish, top predators. And we see much higher mercury than in the invertivores. And also, again, less spatial variation. If you think of this kind of, what is this telling us spatially, it's not really very interesting. So a final set of maps, mercury in whole small fish, which we could call prey fish or a forage fish, in relation to guidelines levels for, or thresholds for various wildlife species, and also the fish themselves and an arbitrary higher level. But basically what we can see here is, first of all, we've got a nice wide distribution of mercury data in these small fishes, widely distributed across the state. We see some really strong regional patterns, again, with those higher concentrations in the Adirondacks and in some other highlands areas. And again, greater spatial heterogeneity than most of the sport fish, suggesting that these small fish would be good mercury biosentinels. So now I talked about the mercury site scores. Again, we're going to try to, with these site scores, examine statewide patterns using data across species and size class, kind of normalizing them to this index or score. So here's the map of these 179 sites with the scores in classes with the darker circles as higher scores. We notice a few things. We see some regional patterns. Again, the scores tend to be very high in the Adirondacks, but at the same time, we see some Adirondack sites with low scores. And also we see some high scores elsewhere. And finally, urban streams tended to have lower scores. And I've got a few of the urban areas circled here. So now we want to look at what drives these patterns, now that we've been able to look at these patterns across the entire state. So we conducted a principal components analysis to try to use mercury relevant variables and try to identify some environmental gradients. But we first created two broad regions, figuring that we might have different gradients across more rural ecoregions of the state and more developed ecoregions. So we've got the uplands shown here in the circles, which are the more rural ecoregions. And then everything else we called the lowlands, and these tend to be the more developed ecoregions. We selected mercury, what we thought were mercury relevant variables, 8 variables shown here in the left column. Most of them were derived from stream stats. And because of that, we have a variable called storage, which includes wetlands, but not only wetlands, but also ponds and lakes. So I just wanted to point that out. And I also wanted to extend appreciation to Huiting Mao for providing the mercury deposition data to us. So looking at the principal components analysis results, the gray squares are the sites. And what I'm going to show next are the variables indicate that the most important variables on the primary axis, principal component axis 1, are going to be shown in red. The most important variables on the secondary axis in each case are going to be shown in bold black. And that will help us interpret these gradients in terms of environmental gradients. So in the lowlands, the primary axis, was a gradient from left to right of increasingly rural watersheds, which also corresponded with somewhat increasing of stream size. So going from more developed to more rural. On the secondary gradient, going from the bottom to the top, shows a shift from higher elevation streams to lower elevation, more impervious surface, so more urbanization, to which there is more atmospheric deposition. So in this case, the atmospheric deposition is associated with impervious surface. So this is atmospheric deposition to urban areas. In the uplands, we see two primary gradients. One is the primary gradient, or two gradients. The primary gradient is a shift from more developed to more forested sites in higher elevations. And the more forested sites, this goes all the way to 100% forest sites. The secondary axis, or can be interpreted as a gradient of decreasing channel slope, and increasing atmospheric deposition associated with increasing storage, or primarily wetlands. So in this case, atmospheric deposition is not associated with deposition to urban areas, but instead deposition to, it's a gradient of deposition to forested areas. And I picture this as the sites that would be way up at the top would be like sites in the Western Adirondacks that have low gradient stream channels, many of them, high atmospheric deposition, and a lot of wetlands. So now we want to ask which of these environmental gradients are related to mercury in fish. And here we see in the lowlands, only the primary environmental gradient was associated positively with, correlated with the fish mercury site score. So fish mercury site score increased with increasing forest and storage, but it did not, was not related at all to increasing atmospheric deposition. Primarily, one would imagine, because it's deposited to impervious surface. In the uplands, we see that the fish mercury site score was positively correlated with both of the environmental gradients. So fish mercury site score increased with increasing forest and elevation, and also with increasing atmospheric deposition and storage. Again, storage is an indicator of wetlands in part. So in summary, we've seen from this broad spatial analysis that mercury in fish from many New York streams and rivers exceeds guidelines for human health and wildlife health. Trophic position, as expected, is a major driver, major biological factor. Small fishes, what many would call prey or forage fishes, are widely distributed and tend to exhibit more spatial variation than some of the larger and more predatory game fishes, and might be better environmental or mercury biosentinels going forward. And watershed forest and storage are important drivers of streamfish mercury in both the lowland and upland regions of New York, indicating the importance of landscape methylation potential to mercury in fish from New York streams. But atmospheric mercury deposition was only an important driver in the uplands, not in the lowlands, due to, we suspect, limited methylation potential of the urban landscape. So this further highlights the importance of methylation to the streamfish mercury patterns. So again, for more information, you can contact me or take a look at the paper in Ecotoxicology.
Okay, thank you very much, Karen. Very interesting talk, and thank you for sticking with us to the end here. I do see a comment and a question in the chat box from Tanya Williamson. What does impervious area provide relative to developed area, and how are they different? Or is D area drainage area?
D area is drainage area. Impervious area, I mean, we have a lot of some areas across the state that would be watersheds that would be considered not highly forested, but they would be agricultural or kind of rural areas, suburban areas, for example. The more highly impervious would be in the more of the larger cities. So increasing impervious would be increasing cities, I would think, or increasing urban areas. Urban industrial, impervious tends to go along with urban industrial. So you kind of have more general development and including suburbs, agriculture, urban, and then you have more kind of urban focused, I think, which would have the impervious surface. I hope that answers the question.
Okay, thank you. We have a comment from Greg Weatherby. Really cool study and a great paper.
Thank you.
Let's see here. We have a question from Rogelio. It is clear that the levels of mercury detected are well compared with those maximum for human beings. Rogelio, I will, if you want to unmute your line and chime in, I don't think I got your question right there, but feel free to ask it yourself. Okay, we're gonna move on. Greg Weatherby has a comment here and a question. So more impervious drainage has less water residence time, thus less wetland areas to methylate mercury, right?
I think that's a big part of it. I also think that the more impervious area, you are also having less, less areas with soil where methylation could occur. I guess that is the same thing basically. Yes. Yeah, you have less soil. It's roofs and pavement and parking lots, and yeah, you know, the mercury falls onto these surfaces and winds up in the water, but it doesn't wind up in the water as methylmercury.
Okay, thank you, Karen. There are a couple of more comments in the chat box. You can take a look at there and answer those if you like. I would like to thank all of our speakers from this last session of the afternoon. A great way to round out the first day of the Science Symposium. A set of very interesting and diverse talks. I want to thank you all for a great set of talks. Now I'll turn it back over to Greg Weatherby for any final comments of the day.
Yeah, thanks everybody for sticking with us and for participating today. Thanks to all of our speakers once again. This has been really great. I hope that everyone had a great conference today, and we've got more coming tomorrow.